Everyone, David Ostrowski here, MCS 2534. It's week 9. We're into chapter 9 in our associated textbook, and I have a different resource that I'm referencing here for disjoint sets. Kind of start from the beginning once more, but take a slightly different viewpoint as disjoint sets and how they can be applied and used in applications and slightly different explanations. So hopefully this will help solidify your understanding. So let's get started. So let's look at the definition here of a disjoint set. So suppose we have an application that involves n distinct items. We will not be adding any new items nor deleting any items. Our application requires us to partition the set into a collection of sets such that each item is in a set and no item is in more than one set. We looked at that in the last example, right? So examples would be students according to class rank, or students according to perhaps their GPA, right? You'd only be in one category, and if you're going to partition that set, right, you would have the no existing items in that set in more than one category, right? So the resulting sets are said to be disjoint sets. Some of the terminology here, we identify a set by choosing a representative element of the set. Doesn't matter which element we choose, but once chosen, it can't change. So there are two operations of interest, and that would be at the abstract level a find and a union. So the find of x, as we've seen before, right, determines which set x is in. Here, the return value is the representative element of that set. A union on x and y, you would make one set of the other set containing x and y. Here, disjoint sets algorithms are sometimes called union find algorithms. Here's an example. Given a set of cities C and a set of roads R that connects the two cities, determine if it's possible to travel from any given city to another given city. So for each city in C, you put each city in its own set. For each road x of y in R, if the find of x is not equal to the find of y, then I'd union x and y. Now we can determine if it's possible to travel by the road between two cities, C1 and C2, by testing the find of C1 if that is equivalent to the find of C2 through the association, right? So here, a simple data structure for implementing disjoint sets is called uptree, right? Here we have W, A, and H, just in the prior examples, they belong to the same set. We're relying on a tree representation with H as the root. In similar fashion, X, B, R, and F, and notice there's no repeats here, right? The X is the representative or the root of that specified tree, with the other three being children nodes, and we're not relying on a strict binary tree here, obviously, right? Operations in an uptree, the find is easy. You can follow the pointer to the representative element. Here, the representative has no parent. A find of x, and the parent of x is not the representative. You would return a find on the parent of x. Otherwise, we return x as the representative. Union, however, is more complicated, right? We can make one representative element pivot to the other, but in which way? It doesn't matter. In the example, some elements are now twice as deep as they were before. We do a union of x and h and x. And here we simply point x to h or h to x. And let's just take a step back to see what we started off with, right? And here's before. We can union these two together by making x the root of all the values, or the h as the root of all values. And that's simply done by associating the root of the original to either one of the other root or correspondingly in the same fashion. This creates some different dynamics as far as searching, obviously, because here the x would being no longer being the root, and the b, r, and f are going to be deeper, and in some nature a, w would be deeper. Worst case for union, the union can be done in big O1, but it may cause that find to become big O of n, right? And again, a lot of it depends on your specific use case, right? So you consider the result of the following sequence of operations: union of A and B, C of A, D and C, and E to D, right? We'll look at an array representation of an up tree. Here we assume each element is associated with an integer. From now on, we deal only with I, and we create an integer array, S of n. Here, an array element is the element's parent, and S of I equal -1 signifies that the element I is the representative element. Union / find with array. Now the union algorithm would be taking the two roots as input and make the association, attaching root 2 to root 1 as we saw illustrated in the diagram. And the find algorithm would take the find and recursively identify itself on when, or invoke itself, right? You return the find or return the x, where the S of x is less than or equal to 0. Improving performance are two heuristics that improve the performance of union find. This would include path compression on find and the union by weight. Path compression: each time we find an element E, we make all the elements on the path from E to the root be intermediate children of the root by making each element's parent be the representative. Here I take find for the integer of x. If S of x is less than 0, return x, otherwise S of x is equal to the find, or return the S of x. Path compression is used. A sequence of M operations takes big O, M log n time, and amortized time is big O n log n per operation. Union by weight heuristic. We always attach a smaller to larger tree, and that would mitigate the extra inefficiencies that are associated with the finds, right? If you're going to take the smaller tree as opposed to the corresponding larger tree. So here you have the weight, and you follow through with the appropriate logic. You have a representative root, performing a find on the root. And if the weight of the representative root of 1 is less than the weight on 2, you make the association of 2 to 1, otherwise 1 to 2, and that was represented in R, and you add the weights appropriately. But you can see with the diagrams that you're going to find the efficiencies there. Performance with union by weight. If the unions are performed by weight, the depth of any element is never greater than log of n. The intuitive proof: every element is at depth 0. An element's depth only increases as a result of a union operation if it's in the smaller tree, in which case it's placed in a tree that becomes at least twice as large as before the union of two equal tree sizes. Here only log n such operations can be formed until all elements are in the same tree. Therefore, find becomes big O log n when union by weight is used, even without path compression. Performance with both optimizations. When both optimizations are performed, a sequence of M greater than n operations, union of finds take no longer no more than big O m log n time. The log n is iterated base 2 of logarithm n. The number of times you take log n before n becomes less than or equal to 1. Union find is essentially the big O for the sequence of m operations, amortize big O of 1. So union find could be applied in a number of interesting operations. Among that is a random maze generator can be used. A union find, consider the fact that if you have a maze, it is essentially taking a matrix and appropriately breaking it down right into separate disjoint sets, right? So I have an in and out, you have an entrance and an exit of this basic matrix here. Here, if you want to generate a maze, you can randomly remove walls until the entrance and exit cells are the same set. Removing a wall is the same as doing a union because you're bringing in you're joining sets right together. If you remove walls, the same as doing a union operation. You do not remove a randomly chosen wall of the set if it separates. If the separates are already in the same set, there's no purpose in removing the associated wall. So here's the make maze operation. And I have the size as input, and entrance, exit. Those are the top, upper left, and lower right. And I do a find entrance, while it's not equal to find the exit, and take randomly chosen cells. And essentially what we're accomplishing here, right, is asking the question, do I actually create a new union, new opportunity for a union operation? Otherwise, it's not going to make any sense to remove that given wall. Here, as it starts, you're always going to create a new set here. You're not going to be duplicates if I remove, let's say, the wall between 1 and 2, or 7 and 12, or 7 and 22. You're going to have the associated disjoint that's created here, and it's going to be, it's going to create a different set. If I look between 8 and 13, that doesn't create a different set. Why? Because it's not bringing any new sets together. So that would be an intermediate state that wouldn't be considered here. We're assuming you've already gone through the algorithm at some point, removing random walls and creating, and this is the only really the only wall at first glance, right, that you have that particular dynamic. You can see that here. If I remove 8 and 13, it's going to be a wash. Okay, so it's not worth happening. It's not going to create a new set, so there's no purpose in doing that, because you've already, by removing between 9 and 14, for example, you've supported the same dynamic. Now, if you had 9 and 14, that wall still existed at 8 and 13, then it would create a disjointed set. So again, to give you an idea, some of the real-world applications has applied correspondingly with pathfinding algorithms and a lot of unique problems that that you can incorporate disjoint data sets as an abstract data type. So thanks for listening. More to come. Any questions, feel free to reach out to me. Take care. Talk to you soon. All right. Bye.